Welcome, my dear students, this new class. The last class we discussed some examples of eigenvalues and different types of eigen matrices. We use diagonal matrices. Eigenvalues are the diagonal elements. We have any triangular matrix, either upper triangular, lower triangular, or diagonal matrix. This eigenvalue always is the diagonal element, and we show that if the symmetric matrix of a real entity, then eigenvalues always is a real. If a non-symmetric non-symmetric matrix, then the eigenvalues maybe is the real or the complex conjugate pairs of this thing. Okay, in this class we start with the, and in the end of the last class we discuss about the right basis. We calculate the eigenvectors, and then all the eigenvectors we can calculate. These eigenvectors are these are the linearly independent and they form a basis. So now in this class we discuss about the some basic properties of eigenvalues and eigenvectors, and then okay, so we start with the first we stop is there. That means we can say that a square matrix A is invertible if and only if lambda is equal to 0 is not an eigenvalue. So that is very clear. A square matrix is invertible if and only if lambda is equal to 0 is not an eigenvalue of A. So we have to just giving the proof of this. Assume that A is a n by n matrix, and observe that first lambda is equal to 0 is a solution. Then the characteristic equation of this we have a lambda to the power n, lambda 1 x to c1 lambda to the power and so on, lambda is equal to 0. So this is the characteristic equation of this, and this the constant term is equal to, you have a 0 if and only if the constant term is equal to 0. This suffices to prove that A is invertible if and only if Cn is not equal to 0. So this means we have to just show that this Cn is not equal to 0, then we can say that A is invertible, and we have to just starting from there. So but determinant of this you have to write into this form. A determinant of a lambda I minus A is equal to lambda to the power n c1 and to Cn. Now setting lambda is equal to 0, you have a determinant of a minus A is equal to Cn, or we can say the minus 1 to the power determinant is equal to Cn. That means determinant of a this is equal to not 0. It follows that from the last equation that determinant of A is equal to 0 if and only if we have a Cn is equal to 0. This implies that A is invertible if and only if Cn is not equal to 0. So that means we can just complete the proof of the theorem. We can say that if by this equation we can say that this matrix is invertible in the case only when Cn is equal to 0, and this is determinant of this is 0 if and only if Cn is equal to 0. So this means this matrix A is invertible only when Cn is not equal to 0. So this means we have to just complete the proof of this. So now we have to come to the this theorem. This theorem says that eigenvectors with distinct eigenvalues are linearly independent. You just remember in the last class, the last exercise, we have to find the basis for lambda is equal to some eigenvalues be corresponding to the eigenvector, and both the eigenvectors are giving you have a linearly independent. So you just say that if we have a v1, v2, vk be eigenvectors of a matrix A, and suppose that the corresponding eigenvalues lambda 1, lambda 2, lambda k are distinct. This means all this lambda are distinct, no equal. Then the v1, v2, vk are linearly independent. That means we can say that corresponding to lambda 1 we have eigenvector is equal to v1. So we have just say that e1 is equal to a v1 is equal to lambda a into lambda 1 into v1. Corresponding to the v2 we have a v2 is equal to lambda 2 v2. Then we can say that, and similarly we can say that a of vk is equal to lambda k and vk. Then we can say that if suppose the corresponding eigenvalues are this, so v1 के corresponding eigenvalues are lambda 1, v2 के corresponding eigenvalue lambda 2, and vk के corresponding lambda eigenvalues is lambda k. Then we can say that these v1, v2, vk are linearly independent. You know that the technique for this, if we show that these are the linearly independent, then we can write a linear combination of these vector alpha 1 v1, alpha 2 v2 plus so on, alpha k vk is equal to 0, and we show that these are the linear combination of these vectors are trivial. For trivial case we can say that lambda 1 alpha 1 up to alpha 2 and so on up to alpha k is equal to 0. If we succeed to prove that this is equal to 0, then we can complete. So we have to try to prove this result by the mathematical induction, because you know that the eigenvector is always not equal to 0. So V1 is not equal to 0 vector. So if V1 is not equal to 0 vector, then we can say that clearly you have a V1 is a lambda 1 is the eigenvalue for this. So a V1 is equal to lambda V1, and V1 is not equal to 0. So is clearly V1 is linearly independent. So we just say that proof mathematical induction. Suppose n is equal to 1, then V1 is not equal to 0, and V1 is an eigenvector. So this V1 is linearly independent. Now we assume that the result is true for n is equal to k minus 1, and then we have to prove that the result. Assume that the result holds for n minus 1 at distinct eigenvalues. So n minus 1 should be strictly greater than equal to 1. So we have a n eigenvectors V1, V2, Vn corresponding to the distinct eigenvalues V1, V2, lambda 1, lambda 2 up to lambda n. Now we have to show that this result holds for all n distinct eigenvalues. So we wish to prove that these vectors are linearly independent. Now we have to just write alpha 1, alpha 2, alpha n are the scalars. So we just write into alpha 1 V1, alpha 2 V2 n is equal to 0. Then we can write this can be written in the form of a we write in the form of a times of a you have a alpha 1 V1 and so on. We just apply here. So we have to apply alpha and lambda n both the sides. So a alpha 1 we just take a lambda 1 up to lambda 2 and then so on. They just apply into this. I just write into this form like this. We have to apply into both sides. So we can just say that a of minus lambda and I, and then we can say that into alpha 1 V1 and so on. And this is we can say right in alpha 1 a is you have the coefficient matrix. So this means a of this is alpha 1 with a V1 is equal to, we can write a of alpha 1 and V1, and then you can say alpha 1 times a of V1. A of V1 can be written as a alpha A1 is equal to lambda 1. So a can be written as a we have a lambda 1 into V1. So this can be written as a alpha 1 into lambda 1, and then we have a last term is equal to we have only this alpha n. So just we have to a minus lambda n. So we have to just take a lambda times of a V1, and then we just write, okay, just clearly is this we can apply into this form. So this we get a minus lambda lambda n I, and then we can say that is equal to alpha times of a V1 plus a minus lambda n I alpha times of alpha 1 alpha 2 times of a V2 and so on. We can say that in the last we can say that we have a times of a minus lambda n I, you have a alpha n minus 1, and you have a v n, and then what we choose that we just said that lambda n into this. So we just write a alpha 1 V1 corresponding to this is equal to this. So this means we can set alpha 1 and we have a V1 and minus lambda I and this. So this means can be written as this a and a vi is equal to lambda 1. So we can just set a of lambda alpha 1 a of vi. This can be written as alpha 1 lambda 1 v1. So this can be written in the form of this first term. It can be written in the form of alpha n is common. We can just say that lambda lambda 1 minus lambda n v1 and plus so on. The second we can write similarly alpha 2 lambda 2 minus lambda n and so on. And then we have a nth term. We have to getting the this is when getting is 0. So we have just a term up to the n minus 1. So we have only the term up to n minus 1, where we have to this we say that this lambda n and this is equal to n vn, and then we can write you have a of alpha n of a of is equal to vn minus lambda times lambda n vn, and then we can say that alpha n, and this can be written as alpha is equal to lambda times vn and minus lambda n vn minus lambda n vn, and this is equal to 0. So last term is eliminating here. So this term is eliminating. So we have only the terms are there this thing, and now we assuming that this with this from here result is true for n is equal to 1. So this means all the n minus 1 vectors are linearly independent. So this means we can say that but the induction we have v1 v2 and as is a linearly independent. So if these are the linearly independent, that means we can alpha 1 lambda 1 m is equal to 0, then this is equal to whole thing is equal to 0. So now because you know that we have to just say that lambda 1 is not equal to lambda n, and we have to lambda 2 is not equal to lambda n, because all of them are distinct. So if we have to lambda 3 is not equal to lambda n, and so on, lambda n minus 1 is not equal to lambda n, because all of them are these are the eigenvalues are distinct. So this means if this is equal to 0, we can say the alpha 1 of lambda 1 minus lambda n is equal to 0. This implies that either alpha 1 is equal to 0, or you can say that lambda 1 minus lambda 1 n is equal to 0. This is not possible. Why? Because these two eigenvalues are distinct. So only possibility is what? Alpha 1 is equal to 0. Similarly, from here we have either alpha 2 is equal to 0 or this thing is equal to 0. This is not possible because these two vectors are linearly they are all are distinct. Similarly, this is equal to 0 and this is clearly is not equal to 0, again because lambda n minus 1 and lambda n are distinct. So what we got, we getting up to the all the vectors up to lambda alpha 1 alpha 2 up to alpha n minus 1 is equal to 0. So this means we have to all the vector alpha n 1 is equal to 0. Now if we are substituting these values in this equation, so we ultimately getting what alpha n vn is equal to 0, but we know that well vn is not equal to 0 because of the eigenvectors. These are the eigenvectors. The only possibility is this is equal to alpha n is equal to 0. So consequently we can say that lambda alpha 1 alpha 2 up to alpha n minus 1 0 from here, and alpha 1 and alpha n is 0 from here. So we can say that all the alpha 1 alpha 2 up to alpha n are as 0. So it follows that v1 v2 vn is a linearly independent. So that means this we complete the proof of this result is clearly we can say that this is a result is proved. That means if we can say that clearly, if we have a lambda 1 lambda 2 lambda n are v1 v2 vn are the eigenvector corresponding to the distinct eigenvalues lambda 1 lambda 2 lambda n, then these eigenvectors v1 v2 vn are linearly independent. Okay, so now another very interesting example, we can say that prove that if A is a square matrix, then A and A transpose have the same eigenvalues, and also he said that giving the example to show that A and transpose have the different eigenvector. Very interesting thing, he said that the eigenvalues are the same, but A and A transpose have the, you provide an example to show that the A and A transpose have a different eigenvalues. So this means we can show first is A is a square matrix, A and A transpose have the same eigenvalues, means we can say that if we can say that A of V is equal to lambda V, then A transpose V is equal to lambda of a V, then we can say that if this is the happening, then lambda is the eigenvalue for A and lambda is the eigenvalue for A transpose. So we have to show that if AV is equal to lambda V, then A transpose V is also is equal to lambda V. Okay, so we can just say any square matrix, we know that determinant of a V is the same as the determinant of a B transpose. So we take a determinant of A minus lambda I, and we take this the same as a determinant of A minus lambda I ka transpose. This can be written as a determinant of a, we can say that as A transpose minus lambda and I transpose, then I transpose is itself. This can be written as a determinant of a transpose minus lambda I. So this means we can say that determinant of A minus lambda I is the same as the determinant of A transpose minus lambda I. So that means we can say that lambda is eigenvalue for A and lambda is eigenvalue for A transpose. This means both the determinants are the same. Then we can say that clearly if these two determinants are the same, then the eigenvalues are also same. So we can just say that which has A and T have the same eigenvalues because they have the same characteristic equation. Both have the same characteristic equation. So that means this, if both have the same characteristic equation, this means eigenvalues of A and eigenvalues of A transpose is the same. Now next is a question is we have to find the two write two square matrices, and then we find the A and A transpose and find the eigenvalues because eigenvalues of both are the same. We can find the eigenvectors. Maybe this eigenvectors say that have a different eigenvectors. Okay, we just take these two matrices. Now you just take A and A transpose. This is the two matrices, and now if you just take eigenvalues of these are the triangular matrix. So this is eigenvalues of both the matrix are the 0 0. So this means both the matrix eigenvector is equal to eigenvalues are is equal to 0. So if eigenvalues is equal to 0, then we can say that 0 1 0 0. Then we have to just say that x and y, and then we can write is equal to 0 0. This form we have a if lambda is equal to 0, so you have a getting this form. So this means you can say that clearly you have to getting this x, you getting y is equal to 0 in this case. So in this case we have a, if lambda is equal to 0 corresponding to a, the eigen vectors are in the form of a, you have a t comma 0, where we can just s is in the form of a d, such that t is the element of some r, or in special case we can say that in particular 0 and 1. In case of this, this is a span of this, and now we try to find the eigenvalue, eigenvector corresponding to this matrix 0 0. So we can say that 0 0 1 0, and this can be written as x and y is equal to 0 0. So we can say that this is equal to this is x is equal to 0. Now if we have a x is equal to 0, then we have a eigenvector in the form of this, you have a 0 and you have a t, this form, and then such that t is the element of some r. So in this case we can, the span of this nothing but is equal to form the, we can say in the form of a, you have a 0 and 1. So clearly here is a 0 and 1 is the eigenvector, here is a 1 into 0 is eigenvector, but the eigenvalues of both the matrices are the same, but eigenvectors of both the matrices are the different. So that means this is the example, we can say that A is equal to A and A transpose have the same eigenvalues, but they have a different eigenvectors. Okay, so this means we can say that span of this A transpose is equal to this. So A and they have the same eigenvalues, but different eigenvectors space are there. Okay, so now we just take a, if we have a lambda is the eigenvalue for A, x is a corresponding eigenvector, and s is a scalar, then a lambda minus s is an eigenvalues of a minus si. So if we have to just say that lambda is an eigenvalue for a minus si, then we can say that of a minus s, x is a corresponding eigenvector. So we just say that lambda is eigenvalue for a, so we can say that ax is equal to, you have a lambda x, and this can be written as a minus lambda I into x is equal to, you have a 0, and then we can say that you have a s is a scalar, the lambda minus s is the eigenvalue for a minus si. So if we just say that we can take a minus si of x is equal to, can be written as a x minus s of I x, and ax is equal to, you have a lambda x, so lambda x minus s of I x, this can be written lambda minus, you have a s of I of x, then this is the same as a, you can write in the form of a lambda minus s x. So this means we can say that a minus six can be written as a lambda minus s into x. So this means we can say that clearly lambda minus s is an eigenvalue of a minus lambda si. This is the proof is complete. So we can show that this is proof is very trivially x lambda x, then we are just taking into this form. So a minus s, lambda minus s is eigenvalue of a minus s of I, where ix corresponding to the eigenvector of this. Okay, now if we have a lambda is an eigenvalue for an invertible matrix A and x is a corresponding eigenvector, then 1 upon lambda is eigenvalue of A inverse and x is a corresponding eigenvector. So we have a x is equal to, we have a given lambda x, lambda is the eigenvalue for A, and lambda is the eigenvalue of an invertible matrix A. If A is an invertible matrix, then we can find the eigenvalue of this is corresponding to A inverse is corresponding to this form. Okay, this is trivial again, we just take by this method, ax is equal to lambda x, we just because A is invertible, we can multiply it by both sides is a inverse, so we can just say that, we can say that A inverse ax can be written as a inverse, we have a lambda x, then this can be written as a inverse a x is equal to, we can just say that we have a lambda times a inverse x, and this is a inverse x is equal to I times x is equal to, we can say that lambda times of a inverse x, and now this can be written as a inverse x is equal to 1 by lambda times x. So we can say that 1 upon lambda is an eigenvalues of a inverse is by the because invertible matrix, so this means a lambda should be not equal to 0 clearly, because lambda, if he is invertible, then we can contradiction this. So A is a lambda is an invertible matrix, so lambda should be not equal to 0, so we can divide by the lambda. So this means we can say that this is the case is equal to this thing. So we multiplied by this, then you can just set Ix into equal to this, then dividing on a scalar. So this is equal to this. So lambda is an eigenvalue for n invertible vertex A, x is corresponding eigenvector. Then 1 upon lambda is an eigenvalue of A inverse, and x is corresponding to the eigenvector is there. Okay, so now we just one more, and suppose lambda is eigenvalue for a matrix A corresponding to the eigenvector x, then k is a positive integer, then show that lambda to the power k is eigenvalues of a to the power k. First we show that suppose lambda is eigenvalue for A, then we try show that lambda square is an eigenvalues of a square. So we just take if we have now A of corresponding eigenvector is x is equal to lambda x. If we have to multiply both sides A, so A x is equal to, we have a times of a lambda x, and this is, you have now nothing, A square x can be written as a form of a lambda times of Ax. Now lambda times Ax, lambda is nothing but is equal to Ax is equal to lambda x, so lambda x, this can be written as a lambda square x. So if we have a, we can say that from here, if lambda is an eigenvalues of values of A, then lambda square is eigenvalues for A square. If we can say the lambda is eigenvalue of this lambda cube also, we can just say that A cube power 3 of x can be written as a times of a square x. This can be written as a times of a square x is equal to, you have to just say that lambda square x, and this is lambda square times A of x. This can be written as a lambda times of lambda x, then this can be written as a lambda cube x. So in the similar fashion we can prove this in this way. We can say that if lambda is eigenvalue of a, then lambda square is eigenvalue for A square, lambda cube is eigenvalue for A cube. In general we can say that lambda to the power k is an eigenvalue for A to the power k. So we just assuming this prove this in this form, and then we can just substitute here Ax is equal to lambda x. So this can be written as a to the power k minus 1 lambda x. This can be written as a lambda times of A to the power k minus 1 x. This can be written as a lambda times of A to the power k minus 2 and A of x, and then again we have a lambda times A to the power k minus 2 lambda x. This is nothing but is equal to lambda square A to the power k minus 2 x, and then the similar fashion we go in the end. We can say that lambda to the power k minus 1, and then we can say that Ax this is lambda to the power this k, and we have to getting x is equal. Okay, so this is k minus 1 lambda x. I just say that. Then we can again this, and then this can be written as a minus 2, and then substitute here lambda x. Then we substitute here k to the power n minus 2, and then so on. We come to writing lambda to the power k minus 1 Ax, and then next term is equal to lambda to the power k minus 1, and then Ax is equal to lambda x. This is equal to lambda to the power k into x. So we can say that this result is true in the case when we have a lambda is an eigenvalues of any matrix A corresponding to the eigenvector x, then A to the power lambda to the power k is eigenvalue of a matrix A to the power k. Okay, so now just in this question, if we have a be a square matrix and G T be a polynomial, if lambda is an eigenvalue of A with eigenvector V, AV is equal to lambda, G lambda is an eigenvalue of a GA with the same eigenvector. So we have a giving the vector is equal to G of A, V is equal to G of lambda V. We have to prove that this form. Okay, so we starting from GT be a polynomial. So I take a this is a polynomial in the form A naught A1t up to A2 AM to the power t. Now we can calculate the G of A with the A, all of them is A. So A square and A to the power m. Now we have to write G of A into V. This is can be written as A naught IV plus you write A1 AV plus you have A2 A square V and plus so on AM A to the power mv, and this can be written as A naught IV plus A1. We have AV is equal to, we have that is equal to lambda V. So lambda V plus A2 A square V means you have a lambda square V, and plus so on we have AM lambda to the power mv. Okay, so this means we can just multiply it by V, and then we can using this condition, and then we substitute the value for this is lambda up to this all V, and this is nothing but is equal to what? This is nothing but is equal to, you have a G of lambda. So this can be written in the form of G of lambda into V. So if lambda is an eigenvalue for A, and we have a GT is any a polynomial, then GA is a eigenvalue, then G lambda is an eigenvalue for G of A with the corresponding to the eigenvector V is a non-zero. So V is an eigenvector of a GA with the eigenvalues of a this thing. Okay, so now just try to one more question, and then we have to go to the stop. For a square matrix, lambda is equal to 0 is an eigenvalue of A if and only if A is a singular. So we just say that this means eigenvalues of this. So we just first we assuming that lambda is equal to 0 is an eigenvalue. Then there exists a non-zero vector V such that A of V is equal to 0 into V is equal to 0. So A of V is equal to 0. A of V 0 means V is the element of a kernel of A. And if V is the kernel of A, V is not equal to 0. So kernel of A is not equal to 0. So which kernel of A is not equal to 0 means A is not injective. If A is not injective, then we can say that A is not invertible. And if A is not invertible, then we can say A is non-singular. This is the proof of this thing. So this way we can prove this. We can just by using I already showed that we can this equivalent condition for null space of A should be not equal to 0. So we can say that this is clearly if it is non-injective, then clearly we can say that this is A is not invertible. If it is not invertible means A is a singular matrix. Now if we have to just say that if A is a singular, then it is not injective. So kernel of A is not equal to 0. That there exists a V such that AV is equal to 0. So by the definition means 0 is an eigenvalues of A with vector eigenvector corresponding to a V. Okay, now evidently if we also show into this form, we have to take a determinant of this. If we have a determinant of A minus 0 dot 1 0 is equal to determinant of A, and determinant of A is equal to 0 means clearly A is a singular matrix. By the in terms of this we can also showing into this form. So that means we can show into this form clearly. This way we can calculate the this result. Means we can say that if lambda is equal to 0, then the matrix A is a singular matrix, and if his matrix is a singular matrix, then the eigenvalues of A is equal to, we have a getting is equal to 0 if and only if condition is there. For a square matrix, eigenvalue of A if and only if A is a singular. So this means if A is a singular, then the eigenvalue should be a 0, and if A is lambda is equal to 0 is eigenvalue of any square matrix, then A should be a singular. So that means this I just say that is complete the solution of this problem also. Now I have to stop today's class at this point. In next class we try to discuss about the how to diagonalization by using the eigenvalues, eigenvectors. So we have two eigenvectors are here, and all the eigenvectors they are formally linearly independent. So we can write the eigenvectors as a matrix of a columns of all this matrix, and then we find the invertible matrix. This invertible matrix can be diagonalized the matrix also. So if we diagonalization of a diagonal of a matrix means we have only the diagonal element of a matrix is called as a diagonalization of this thing. Okay, so we just stop today class here and continue into the next class about the diagonalization of a matrix. Okay, thank you very much.